Hello. Today we're going to talk about logical gates. That's a topic in chapter 10 in our textbook. Logical gates are implementations of Boolean functions. Now, what is a Boolean function? A Boolean function is a mathematical function, similar to functions that you studied before. You have the domain, you have the range, but the domain are made of only zeros and ones, and so is the range of the function. So here's an example of a Boolean function, and this is a domain that has two variables, two inputs, and then one output. So here, if the domain is made of zeros and ones, then we can list all the possible elements in the domain. So if x can be only 0 or 1, and y can also be 0 or 1, then we have four possibilities, four elements in the domain. And for each element of the domain, we have an output. Now, you may ask here, what is a formula for that? Well, formulas are mathematical expressions that will define relationships between outputs and inputs, and that's usually for domains that are infinite. So what I'm trying to say here is that, for example, in the traditional algebra, right? Look at this example here. This is very familiar to you, right? We have the domain being these numbers, and then the range or the outputs are 2 times the element in the domain. So if the element is 3, the output is 6, and we have a formula for that. So you can describe the function, you can define the function in terms of a formula. So you don't need to list the elements in the table, okay? But only if you know the pattern here, right? So, and formulas are useful when you have infinite number of numbers in your domain, and you need to, for each element in the domain, you need to define the outputs. For Boolean functions, you don't need a formula because we can simply list all the possible elements in the domain. And for each element, we simply say, this is the output for that, this is the output for this, and so forth. Eventually, it will end because it's finite. Now, logical gates, there are building blocks of things that we use today in computers. With logical gates, we are able to create transistors and using transistors to create computers. So we have now a computer or a laptop or phone device and many other electronic device can perform operations, and the building blocks of those transistors and chips are inside these devices are made of logical gates. Computer memory is made of logical gates. In fact, we're going to see an example of on how we create a building block of a computer memory, using these devices. So it's important to know. It's an important part of discrete math to analyze these basic ideas of logical gates and Boolean functions. It's an interesting application of discrete math. And we're going to look at three basic Boolean functions: the AND, OR, and NOT. For those of you who are familiar with truth tables, this is pretty much the same thing, but we're going to do a little bit more, and we're going to also describe something called Boolean algebra, and we're going to deal with that algebra as well to simplify some of the circuits that you can construct with those ANDs and ORs and NOTs. And that's the application of discrete math that we're going to see. All right. Now, because the number of elements in the domain is, finite, then we have 16 possible logical gates with 2 inputs, right? So here are the 2 inputs, and again, each input can only be 0 or 1, so the total number of possibilities here is 4. And for each of those 4, you can either have 0 or 1 as your output. So you can see that you could have 16 different gates or Boolean functions, right? So one Boolean function, you could have all zeros, right? 0, 0, 0, 0. Another Boolean function can have 0, 0, 0, 1. Another one can be 0, 0, 1, 0. So the total number of possibilities is 2 to the 4th power, right? 16 gates. But of those 16 gates or Boolean functions, we're going to look at 2 of them that are very special. The first one is the AND gate. The AND gate is defined this way. Again, there is no formula. A formula is this. It's the truth table, or it's this diagram here that shows the outputs. So the AND gate works this way. If you have 0, 0, the output is 0. If one of the inputs is 1, if one of the inputs is 0, then the output is 0. So that describes these 3 here, right? These 3 outputs. So look at the domain. If one of the values of the variables is 0, then the output is 0. The output is going to be 1 only if you have 1s in your input, right? And this is very similar to truth tables. If you treat 0 as false and 1 as true, then you can see exactly how this works, right? If it's false, false, then the output is false. If it's false, true, then the output is false. If it's true and true, the output is true. So it's the same thing. And then there's the other gate that we're going to use that is very special. It's the OR gate. The OR gate, it's easy to define as well. If at least one of the inputs is 1, then the output is 1. If both inputs here, x and y, are zeros, then the output is 0. Okay. So one way to define actually is so we can say here, output is 1 only if x is 1 and y is 1. Otherwise it's 0. That describes the AND gate. Okay. And then the OR gate, output is 0 only if x is 0 and y is 0. That describes the gate, the OR gate. Okay. Now, there is one gate with one input, and that's the NOR gate. That's a special logical gate with one input that we're going to also consider. The NOT gate has only one variable in the input as the input. And the NOT gate is very simple. It's the opposite of what you have here. If you have 0 as your input, the output is 1, right? If it's 1, then it's 0. So the NOT gate, it describes the negation, right? It's the opposite. So with those three gates, the AND gate, the OR gate, and the NOT gate, we we'll construct something called the Boolean algebra. Okay. Before we go any further, we need to define symbols for these gates that we defined. So here's the operation. If you have x and y in the book, there is a symbol for that. Here is the caret. This is called a caret. Okay. That's this symbol here. It represents the gate AND, and the OR is the caret upside down, and the NOT it's represented by the apostrophe. Now I'm gonna use this notation here, which seems to be easier because it reminds us of the regular algebra that we're used to. So we can use for the gate, for the AND gate, we can use multiplication, the dot, right? And the OR gate, we can use the addition. And the NOT gate, we're going to keep the same as this one, the apostrophe. And then in the textbook, we can see the list of properties of these gates. So here it is. So this is theorem 10.1 in the book. So that theorem yields an interesting type of algebra. It's called the Boolean algebra. So here in the book, you will see these symbols here, the caret and the caret upside down. But in this handout here, I replaced them with the plus and the multiplication, the plus and the multiplication sign. So here's one of the properties, the commutative property. That's very basic. It works for Boolean, or for the OR and the AND gates. If you do X or Y, that's the same as Y or X. And it works for the AND gate as well. And the associative property also works fine. The distributive property is interesting because there's two types of distributive properties here. You can actually distribute the addition. See, the addition, you can do x plus y times x plus z. This is an unusual distributive property. We are more familiar with this one here, right? This is what we've been using in algebra in most math classes, right? You have x times x plus z. You can simply distribute, right? X times y plus x times z. But in Boolean algebra, you can also distribute the addition, the sum, the addition. You can do x plus y times x plus z. Okay. We're going to look into these properties with a little bit more depth. Okay, so here I'm going to talk about the distributive property, which is kind of tricky because we are not used to that. So the distributive property, this is the normal distribution that we use, right? This is fine. This is okay. X times y plus x times z. But look at this one. This one is a little tricky because we are not used to that. You distribute the addition x plus y times x plus z. Okay. Okay, one comment that I want to make here is that we're going to treat the AND gate here. See that we are using multiplication. If you see AND gate, then you do it first, right? unless there is a parenthesis that tell you otherwise. So in fact, we should have put parentheses here, but if we use the multiplication, then we know that we have to do multiplication first. That's in a regular algebra, right? In Boolean algebra, let's make that same assumption. So if you see something like this, right? I don't know, like something like that, then we're going to assume that we're going to do this first. The multiplication has priority. Okay. If we don't make that assumption, then someone looks at this, and then they will do x plus y first, then it's going to multiply by z. To avoid that, we usually put parentheses, right? So because we want, let's say we want to do multiplication first, then we put parentheses. But if we use the same property, the same concept that we use in the regular algebra, then we're going to do multiplication first. Okay. Now let's take a look at y. This formula here, this expression is equal to this expression there. One way to prove is to simply test all the elements, right? All the inputs. And we can do that because there is a finite number of inputs. Now notice that the formula here has 3 variables. Because it has 3 variables, then this should be x, y, and z. Forgot that. And each variable can be 0 or 1, so we have a total of 8 possibilities. So we're listing all the possibilities here. So we can test each input, each case, and see what the output here is, and see what the output here is, and then see if they are the same. So I'll just do a few of them here so you can see. So if x is 0, y is 0, and z is 0, then what is this? Now remember that the multiplication there is not the multiplication that we're used to do, okay? It's not arithmetic. This is the AND gate. And the sum here, the plus sign, means the OR gate. So we're not doing 2 plus 2 equals 4. We're not doing anything like that. It's AND. So 0 and 0 is 0. So this becomes 0. And then 0 or 0 is 0. And then here you will see that also gives you the same output. 0 or 0 is 0, 0 or 0 is 0, and then 0 and 0 is 0. See, same output. And we can do, let me do, for example, this one here. That would be 1 plus 0 times 1. You can see that this is 0 and 1 is 0, and then 1 or 0 is 1. And here it would be 1 plus 0, 1 plus 1, according to the formula. Alright, 1 or 0 is 1, 1 or 1 is 1, and then 1 and 1 is 1. So we're getting the same things. And it turns out that all of them, right, if you compute all these outputs here, and if you compute all those outputs here, you will see that they match. They are the same. Therefore, this formula is equal to this one. Again, we can prove this way because we only have a finite number of inputs. So we can check all the inputs, which is not, this strategy is not good for domains that are infinite, right? So we couldn't do that, for example, right? So if we have like in a regular algebra, we have something like this, 2x, and then x plus x. Right, we have 0.1, this is 2.0.1, and this is 0.1 plus 0.1. Okay, this is 0.2, this is 0.2, good. Next, let's try 0.0001. Right? It's infinite. There's no way you will never be able to exhaust all these possibilities. If you could, then you would prove that this is equal to that. If we could check every single possibility, but it's infinite. There's no way. So the reason that we know that it's 2x is equal to 2 plus x plus x, it's because it's one of the basic arithmetic properties that you learned in a long time ago. But in Boolean algebra, it's a new type of algebra that you've probably seen that first time. Then we can simply prove the formulas through truth tables. Okay, here's one property of Boolean algebra. It's called the idempotent property. It comes from the theorem here. That's this one here, property E. It says that x plus x equals to x, and this says x times x equals to x. Again, remember that this is not arithmetic. This has nothing to do with the algebra that we learned, in the past. This is simply saying that x or x is equal to x, and this is saying that x and x is equal to x. So let's prove this one here. There. So how do we show that x plus x equals to x? Now, because it's a Boolean algebra, then the x variable can only assume values of zeros and ones. So x can only be 0, 1. Then we can split into two cases. What if x is 0 and what if x is 1? And then see what happens. If x is 0, then you will have 0 or 0, which we know it's 0. So that matches the other side of the equation, the right side of the equation. So that shows that case number 1. Case number 2, if x is 1, then you have 1 or 1, which is 1, and that matches the other side, that is also 1. That shows that x plus x is equals to x, right? Or it really means showing that x or x is equal to x. Here's another one. This is the identity property. That is this property here. There are 4 identity properties. Notice that these 3 here, they look very similar to the arithmetic properties, right? The algebra properties that we saw before, right? X plus 0 is equals to 0. But look at this one. X plus 1 equals to 1. That's kind of odd. But again, these operations are not additions or multiplications. They are or and and. So this is x or 0. This is x or 1, and so forth. Okay, so how do we show that? Well, this formula here has only one variable, x. Again, we can test 2 cases. What if x is 1? What if x is 0? And then see what happens. If x is 0, then this would be 0 or 1, which is 1. And that matches the other side. What if x is 1? Then this would be 1 or 1, which is 1. And that matches the other side. That shows the formula. That shows the formula is true. Alright. Now, Boolean algebra has also an interesting property. It's the last property of the theorem. It's called the De Morgan's law. The De Morgan's law says that if you negate an addition, then it becomes multiplication of the negations. Okay, that's one way to see it. This reminds us of the negative property. Okay, now I said negative, but remember, in Boolean algebra, there's no such a thing as negative numbers or negative things. There's no subtraction here either. There's no division, okay? Because this is not arithmetic. But the Morgan's law reminds us of the this property here that you're familiar with from arithmetic. Right? Recall from arithmetic, if you have negative x plus y, you remember how we did that? Well, that's negative x, right, plus negative y. So you simply replace, you see the sign of x is positive, becomes negative. The sign of y is positive, becomes negative. So the Morgan's law is kind of similar, but it does something to the operation inside the parentheses. So you distribute the negation, so it becomes negative x, or non-negative, sorry. It becomes negation x, or not x and not y. But look at the operation here. Plus, it becomes multiplication. If it's multiplication, it becomes plus, it becomes addition. So it is a little bit different, right? So that's the Morgan's law. And one way to prove the Morgan's law is simply to construct the truth table, right? There's only two variables here, so you can make 4 cases, and then for each case you see what the value of this is, and see what the value of this is, and see if they're equal for all 4 cases. If they are, then this is equal to that. Okay, with those properties we can actually now do some algebra simplification, and this is pretty neat because now we can use all those properties and treat this as a new type of algebra. So for example here, how do we simplify x plus x times y? Well, one thing you can do here is the factoring, right? We can factor x and x from here and from here. Well, but what is factoring in Boolean algebra? Well, we can treat x as x times 1, right? That's one property of the Boolean algebra. And then you can see that this comes from the distributive property. Right? X, it comes from that. If you go backwards, you will see that it's the same thing. X times 1 is this, x times y is that. And here's an interesting thing that happens in Boolean algebra. 1 plus y is 1. That's the idempotent formula. Well, actually the identity formula. The idempotent is this one here. But it's the identity property. If you, this is 1 or y, it doesn't matter what y is, because you always have 1, so it becomes 1. It's the identity property. And then x times 1 is x. So that is equal to x. And look at this one. I can distribute x times x times y, and this becomes x times x. Right? That's the idempotent formula property. Here it is. X times x is x. And then x times y is x times y. And then that is the same as this one. And we know that this is x. Okay. Finally, we also can draw diagrams of these gates. And here's an example of the diagram for the AND gate. So this represents the inputs. You have the input x and y, and then this symbol here It's kind of a half circle, and that represents the AND gate. Here's the OR gate, the two inputs, and here's the output, and then the NOT gate represented by this triangle. And we can do, any Boolean formula expression can be represented by, can be drawn using this diagram. So, for example, that one, x plus x times y. So x is x times y. So how we draw the diagram of this expression? We have x and y. Notice that we're going to do multiplication first. Okay, x times y. So that becomes that, and then once we do and, then we need to do OR with x. So we can either put another line here to represent x, and this will come into a OR gate. Okay. So x and y here, that gives us x times y. And notice that x goes in here, this becomes x plus x times y. So it's okay to repeat the x there, so it doesn't become too messy, right? One thing you could do, if you want to do that, is to pull a little, a line from here, meaning that x also can go this way. That becomes a little bit messier, but the book uses this idea here of repeating the input. Anyway, this is the diagram of that.